So, we are almost towards the end of Cooper's problem, so famous Cooper problem, and we got this relation that 1 is equal to V 0 by L cube sum over k 1 by minus epsilon plus h cross square k square by m minus 2 E f 0. And we converted that to an energy integral using this well known relations, because this function, for example, is a function of just this original the original energies, the energy of the non interacting free electron. This is the free electron energy of basically two particles, and so this is a function of this original epsilon k. So, as I wrote down that any integral of this kind over k, so you have d 3 k by 4 pi cube can be d 3 k by 4 pi cube can be converted to a density of stress integral which is epsilon d epsilon g of epsilon, where g of epsilon is the density of states, okay, of the original particles. So, that is the Fermi sea. Okay. So, that means this equation now becomes 1 equal to V 0 g of E g of E 1 by twice C minus epsilon d of C, okay, where C is defined as h cross square k square by twice m, which is epsilon k minus E f 0 is epsilon k minus E f 0, right. This epsilon k is the original energies of the original fermions, electrons. So, this so I do something that we have been doing all along, is that since we are interested in a narrow region about the Fermi level, and this can be taken. See, this integral has to be within that h cross omega dy window. So, this can be now taken outside by replacing it by its Fermi level value. So, that means that I can write this as V 0 Z E f. So, the V 0 the convention we are following is rho E f into integral over 1 by twice C minus epsilon d C, okay, 0 to h cross omega dy. So, that is now achieved. So, now our life is much simpler. All you have to do is to this integral, which is straightforward, which gives you this, and so there is a logarithmic term. This logarithm will give you this result that you see once you have this. So, let me just write down this result. So, 2 by V 0 rho E f equal to log of epsilon minus 2 h cross omega d divided by epsilon, okay. And that means that epsilon is equal to 2 h cross omega dy divided by 1 minus exponential of this quantity. So, this I will just exponentiate it to get this 2 by V 0 rho E f. Okay. And that means This EF0 is of course the same. I am using EF0. So, let me put EF0 here, that is the non-interacting Fermi level energy of the Fermi level, Fermi energy, and the original Fermi Fermi energy of the original Fermi C. And that now what I can do is that since V0 times rho E effective, rho at Fermi level is much less than 1. Why? Because you see rho of EF is generally usually of order 1 by EF, okay. And then V0 is a very tiny interaction that was generated by that detailed process that we have discussed. So, V0 divided by EF is the scale of this object, and this has to be very small. EF being say 10,000 20,000 degree Kelvin or 1 or 2 eV, and V0 is milli electron volt order. So, there is no comparison. So, you can just keep only one part of the exponential, and then the e to the power, the other part you can replace by e to the power 0. So this okay, sorry about it. What I am saying is that if you can look at it, this is much larger, and this much larger energy exponent can just be this one can just be ignored, okay. And this one is tiny number compared to this exponential 2 by V0 rho EF. So, that is why we will just keep this exponential this, neglect the 1, and the result that you will get is epsilon equal to minus 2 h cross omega d e to the power minus 2 by V0 rho EF, okay. And that is this result. And the important thing is that this sign. So, this sign is what tells us that there is a negative value for epsilon. So, epsilon turning out negative means that you have a state, 2 particle energy state is actually below the Fermi level now. So, the 2 particles which were there, sum of their energies were 2 EFs naught, has now come below the Fermi level. Their combined energy is actually stabilized. So, the original energy and the new energies, amongst them the new one is the lower energy. So, this is really remarkable. This problem tells you that in the presence of a Fermi surface which blocks these states below it, which are all filled up, if you put 2 electrons just above this Fermi surface, these 2 electrons are allowed to interact by this retarded interaction which is attractive, then you will produce a bound state whose total energy is less than the 2 EF naught that the original energy was. So, this is a remarkable calculation in the sense that it opens the path for finding out the full theory of the superconductors, which is what we will now go to. Okay. So, that means it says the ground state of the non-interacting free electron gas becomes unstable when a minute attractive interaction between electrons is switched on. So, this is an instability of the Fermi surface, because the original Fermi surface was all the electrons fill up to EF naught, but now it shows that if you just put 2 electrons right above the Fermi surface, their total energy is such that the bound state will form below the Fermi surface. So, that means the Fermi surface will start becoming unstable, and it just indicates that your ground state is no longer a stable ground state. You have to look for a new ground state, and probably there is a phase transition to a new ground state. So, that is what this theory of BCS undertook to explain, starting from this kind of an idea that the Fermi surface has now become unstable, you have to look for a new many body state which incorporates the idea of Cooper that electrons pair up, and that kind of a ground state was written down by Bob Schrieffer and Robert Schrieffer, and he and then three of them combined to produce this extraordinary theory, which is what I will study now. So, let us see. Okay, so Cooper pair must be imagined as two electrons occupying state k up minus k down, k prime up minus k prime down, and so on, right, with their k vectors opposite and spins are also opposite. So, the trouble is that now you have to consider all the other 10 to the power 23 electrons that are in between these electrons, that are all there. So, it is a big soup of 10 to the power 23 electrons, they are interacting with each other and with these pairs, and in between these electrons which are just above the Fermi level, they are trying to pair up. So, this is a mess of course, but the basic idea is already laid down, and what BCS did was that they realized that you just cannot sum up these minus epsilon energies to get the new energy. That is not what is happening. It is not a sum of all these two particle states, it is not just a product of these two particle states. So that the energy is just a sum of this Cooper bound state energy. That is not the case. You have to be able to write the full many body Hamiltonian and solve it in any way you can, and that is what they undertook to do. And the way they did it is just that they wrote down a wave function for the many body states, and that is what we are doing. So, let us just go about looking at this. Suppose Wk is the probability that the pair state k up minus k down is occupied. Okay. So, that probability is Wk. Then its energy is of course E kinetic is equal to twice Wk Ck, where Ck is just some Ek minus Ef naught. Okay. So, then there are these total energy reduction will happen, and happen due to these scattering processes as we just saw, k up minus k down going to k prime up minus k prime down states. Okay. And there are zillions and zillions of such scattering going on, and the total energy will get lowered. So, what they wrote down was that they wrote down a wave function which is like this, is uk times 0 plus vk times this 1 0k 1k. What does 0k and 1k mean? 0k means a state where the pair is unoccupied, 1k means a pair state where the pair is occupied, right. So, and uk is so vk is the probability of occupying a state k up k down, which is what we have written down wk square. Okay. So, this is sorry, Vk square is equal to the probability Wk. Sorry about it, because we defined Wk as the probability. So, Vk square must be the probability Wk, and then Uk is the probability of singly occupying, no occupation of that pair state. So, that means Uk square then must be equal to 1 minus Vk square. Okay. Okay. So, that is so that is what this state defines. Now, one just takes a product of all such states, all such paired states for all such pairs momenta k and minus k. So, the BCS wave function then is just a product of this kind of a wave function. It is a pair. I mean, it is just a very simple wave function, a pair being occupied with probability v k square and a pair being unoccupied with probability u k square, and such states are now taken product of. So, the BCS state that they predicted is pi over k product over all such k states u k 0 k plus v k 1 k. So, that is it. So, this is the famous BCS state and it worked and that is the beauty of it, that it produced results which are marvelous, which agreed with most of the experimental results of that time, and for old superconductors this really works extremely well. So, that is what we are going to now work out. We will find out, starting from this kind of a state, how the physical properties, different physical properties can be worked out and matched with the experimental values, experimental results. So, one can take a representation as 1 k is equal to 1 0. You can write down a basis function like this, because it is a two level system, just two things. I mean, a level can be occupied or unoccupied. So, if it is unoccupied, its energy is 0. If it is occupied, its energy is whatever we had given, C k. So, twice that, 2 C k. So, that means I again write down this. These such things can always be represented by this. I mean, it is a 2 by in the basis has 2 states. So, I can always represent it by this way, and such states can be then represented by a spin model actually correspondingly, which makes transition between these 2 states, which happens when a scattering takes place by v k k prime, and the 0 k state is 0 1. So, this is my convention, this is how I define. This is the convention here used. Now, you can transform these states between one another using Pauli matrices. These basically Pauli matrices can be used now to define a creation and an annihilation operator, which is half sigma k 1. Sigma k 1 is given here, plus I sigma k 2. So, sigma k 1 and sigma 2 are these matrices. These are well known Pauli matrices, and that is what that's being used here to write down this raising, so called raising operator. What does it do? It basically changes a 0 occupation to a occupation 1. So, it raises this number by 1. Sigma minus is basically, and sigma plus minus is basically this. So, sigma, the operations are then you can define sigma 1 sigma k plus operating on 0 k will give you 1 k, sigma k operating on 1 sigma k minus operating on 1 k will give you 0 k, and sigma k plus operating on 1 k will give you 0. Similarly, sigma k minus operating on 0 k will also give you 0, because you cannot raise it beyond 1, you cannot raise cannot take 0 below it, okay, the 0 state. So, these are things we have done several times in Ising model also, and Heisenberg model and so on, and and in simple harmonic oscillator also we have defined these raising lowering operators, but these are these are like pseudo spins. One can define this 1 and 0 as up and down spin if you like. So, they are formally identical to the spin operators. Okay. So, they are basically creation and annihilation operator of Cooper pairs. Okay. There, of course, the interpretation is very different. They are basically creation and annihilation operator for Cooper pairs, but they are formally identical to the spin operators that we have used many times. Okay, so as I said, the scattering between the k up minus k down from one particular k paired state at k, that means k and minus k occupied, to another state which is k prime and minus k prime occupied, is done via the v k k prime. So, the Hamiltonian should also reflect that as it did in the in this Cooper problem as well. So, all that can be done here using these operators, and this is exactly what this operator does. This operator basically destroys a state in here, for example, if you look at this state half sigma k prime plus sigma k minus, what does it do? It just destroys a pair at k, annihilates a pair at k momentum, that means k minus k, and it creates a pair at k prime, which means k prime minus k prime is now occupied, and this is the Hermitian conjugate of that. So, that is basically, and then since you can again use k and k prime being different, you can use the matrix algebra and commute them, and you will end up with this just one of them is good enough. This is what we did in Heisenberg ferromagnet, remember. There we took the plus k on the right hand side, here we do not need to do that. So, this is how it is written. So, sigma plus k sigma minus k prime times v naught by L cube, of course, sum over all such k k primes is the interaction term that represents the scattering. Okay. Again, remember that this v naught we have to restrict, and v naught has to be restricted again within the shell of h cross omega d by, because v naught cannot work all over the band and over the entire Fermi, all the states below the Fermi level. It only acts in a narrow strip around the Fermi level, and that restriction we have to again keep in mind while doing the integration summations. Wherever k k prime summations come in, we have to remember the corresponding pair's energy must be within that the electrons that originally form the pair, that their energies must be in that range. So, that is a restriction we have to keep in mind. Okay. So, the energy reduction due to collisions is now obtained by just a first order perturbation theory. Again, the V naught being so small compared to other energy scales in the system, one can just do a perturbation theory, and that perturbation theory leads to this kind of a term psi BCS H psi BCS is simply this. This you can work out. This is very simple. Just take this kind of a product between two states, two BCS states, and you will get this result. This is absolutely straightforward. Okay. And therefore, the total BCS energy, total energy has to be summed over all such case. This is the first term we already wrote, the kinetic energy, and this is the second term, is the term coming from scattering, taking k pair state to k prime pair state and vice versa, and all such k primes. Okay. So, that gives you this second term. Now, one interesting thing about BCS wave function that I would like you to notice is that if you look at this wave function UK0 plus V k 1 k pi over k. Now, if you just let us take a look aside, and I just want you to see what this wave function does. So, let us just assume that there are only two k states. So, k 1 and k 2. Okay. So, these so that means this is u k 1. So, let me just not write k 1 k 2, just write 1, which means u k 1. To make notation life simple, I will just write u 1 into 0 plus V 1 1 into u 2 0 plus V 2 1. So, this is in one state 1, this is in 2 2. Okay. Now, let us look at it. This first product is giving me u 1 into u 2 into 2 zeros. So, it says that both k 1 and k 2 pair states are unoccupied. Okay. So, let me just write this as so both k 1 k 2 states are unoccupied. This is the first term with u 1 into u 2. Second is u 1 into V 2. So, the first state is unoccupied, but the second state is occupied. So, this is a state with 2 electrons, which amplitude is u 1 into V 2. Similarly, V 1 into u 2 will have the similar, which is 1 occupied and 2 unoccupied, right. It has 2 electrons again. But then look at this last state product V 1 V 2 1 1 1 1. This has 4 electrons. So, this is a 0 electron state, this is a 2 electron state, this is a 2 electron state, this is a 4 electron state. That means this is 0 pair, 1 pair, 1 pair, 2 pairs. Okay. So, this wave function is actually a sum of all even number of electron states of this kind. So, you cannot have a single electron in this, odd number of electrons are not existing, and also the number of electrons in this state is not fixed. This state is a linear combination of 0, 2, 2, 4 electronic states. So, this is a remarkable state. Normally, we are used to working with a fixed number of states, fixed number of electrons, and this ground state that Bardeen, Cooper and Schrieffer wrote down does not obey that. So, number is not a conserved quantity in this wave function. So, number is no longer a good quantum number. So, this wave function you should carefully handle that this wave function does not conserve the number, and you have to fix the number by other means, which is by using a Lagrange multiplier, which is like a chemical potential and so on. So, that is an aside which I wanted to show you and want you to remember that this is a unique wave function which is not an eigenstate. So, if I try to find out by number operator operating on psi BCS, I will not get something here times psi BCS. Okay. So, it is not an eigenstate of the number operator. So, that is something you should remember and keep it in your mind that this is a very different state from what we are used to in our normal quantum mechanics of many particle systems. There we are told that you have 2 particles or you have 5 particles or you have 10 particles or you have whatever particles, and you write down the corresponding state by taking that many products and so on. but here that prescription is not allowed. You are not doing that. You are doing something very different, and this is why this state is so unique, which we will discuss. The consequences of this we will discuss in the next class.